Hello, in this video we're going to talk about phase diagrams. So a phase diagram shows phase changes, transitions from one phase to another. And the phase diagram summarizes basically at what pressure and temperature are you in each phase. And so I put this picture on to the right here because it shows the names for each of the phase changes. So if you go between a solid and a liquid, you're freezing or melting, and melting is sometimes called fusion. If you go between a liquid and a gas, you have vaporization or condensation. We've talked about that before. If you take a solid into a gas, that's called sublimation. And the reverse process is called deposition. And then if you go in and out of a plasma, it's called ionization and deionization. Now we haven't talked about plasmas that much in this course because in order to be in a plasma, typically you have to be at a crazy high temperature and pressure, which is not something we ever really see in the chemical context. So typically plasmas are more the domain of physics. So here's a phase diagram. On the y-axis we usually put pressure, on the x-axis we usually put temperature. Although you could switch the two, there's not like a dependent and independent variable here. And you have these lines that tell you, okay, on this line is the difference between a solid and a gas. Here's solid liquid, here's liquid gas, and then if you're sitting somewhere here, you're a solid, things like that. So let's do some hypotheticals. Say you're at 1 atmosphere and you have a solid. Since this is water, we'll call it ice. You heat it up. When you cross this line, which happens at 0 degrees Celsius at 1 atmosphere, you then melt into a liquid. And then you keep heating. At 100 degrees Celsius, you'll turn into a gas. And then you can keep heating the gas if you'd like. Okay, straightforward. Now, if you're at a much reduced pressure, you can sublime water. You can go straight from a solid into a gas, and then the temperature at which you do so depends on the pressure and where you cross this line. So say we started at this temperature and went through here, through the triple point. So the triple point is a place where you have a solid, a liquid, and a gas all in equilibrium with each other. So you can simultaneously be melting and boiling your ice, which is kind of cool. For water, the triple point occurs at a pressure of 0.006 atmospheres, and then the temperature is 273.16 Kelvin, or almost 0 degrees Celsius. And this is actually used as the definition point for the Kelvin temperature scale. Say you start up here in a liquid at a really high pressure, and then you heat it up. What happens? Well, you form a supercritical fluid. So you go from a liquid to a gas, but not discretely, right? This line between a liquid and a gas ends at some point called the critical point. And beyond that point, if you try to go through this area, you will just kind of have properties of a liquid that turn into a mixture of liquid and gas-like properties that we call a supercritical fluid. And so it will dissolve solutes like a liquid. It will expand to fill all available space like a gas, and that's kind of cool if you think of it. And so water supercritically is used to decaffeinate coffee, or it can be used to decaffeinate coffee. It's kind of an expensive way to do it, but you can use it for that. Okay, one more thing to talk about. When you have a solid, when you're dealing with water, and you go up, so you increase the pressure, you will turn into a liquid at some point. And so this is really rare for compounds and pretty useful. So the reason why this happens is because the density of ice is less than the density of water, and when you increase the pressure, you will kind of squeeze the substance into its more dense form. So for the case of water, it'll take a solid and squeeze it into a liquid. Now, the fact that water as a solid is less dense than water the liquid is super useful, because when your lake freezes in the winter, the ice stays on top, and because it floats on water. Whereas if it was the other way around, like most compounds, where the solid is more dense than the liquid, your lake would freeze from the bottom up. It would freeze all the way through and kill all the fishies over the winter. So, kind of a useful thing that ice floats on water. Okay, here's another phase diagram. Here's carbon dioxide. The slope, the positive slope between the solid and the liquid is much more typical. You have the triple point there, and just like a kind of standard phase diagram like we were just looking at. So if you start at 1 atmosphere, you'll have a solid. Solid carbon dioxide is better known as dry ice. And then when you raise the temperature above 78 Celsius, it'll sublime and turn into a gas. Another thing about carbon dioxide is that the pressure where you reach the critical point is much lower than most other compounds, and so it's commonly used as a supercritical fluid. So I have a cool picture of this, that if you're doing some organic reaction and you want a non-polar solvent, well, if you want to do green chemistry, so environmentally benign chemistry, if you use some sort of organic solvent, usually they're toxic, and these are just things you don't want to get into if you're trying to do a green process. So you can use carbon dioxide for this. It's a little complicated because you have to do everything in a pressure vessel, but as the pictures here show, you have below the supercritical fluid, you'll have a liquid and a gas. Discretely, you can see the line between them. And then as you heat it up and increase the pressure, you'll turn it into a supercritical fluid where then this dividing line disappears. And this could be used as a solvent for your reaction because it will function like a liquid, but it has some unique properties that could be advantageous for what you're trying to do. Okay, one other thing about phase diagrams is that they can have more than 3 components. You're not limited here. And so here's an example for what sulfur looks like. And if you get really in-depth for water, you can draw a phase diagram that has different structures of ice. That starts to complicate everything. But it is a valid thing you can do for water. We just tend to simplify it and ignore the fact that there are multiple phases of ice with slightly different crystal structures. Okay, and that's all we have on phase diagrams. Thanks for watching.